This is a recording for integration by parts, and one of the things I wanted to show you was how to handle it when what you have is something like this, which is a little bit more complicated than if it were just x squared e to the x. So, or if it was just x e to the x. So anyway, let's get started. Generally speaking, when you do something like this, if you notice this is a polynomial. If I take three derivatives, you're down to 0. So keep that in mind as I go through this. Watch. U, we're going to let be equal to x squared. dv, we're going to let be e to the x dx. Now, that forces du into being equal to 2x dx, and v integrating this is going to give us e to the x. Okay? Now, as by the formula, we're going to have, from integration by parts, it's going to be v times u, which is x squared e to the x minus the integral of v du, which is going to be 2x e to the x dx. So what we've done, integration by parts, made this second integral now a little bit easier to take, so we know that we've probably chosen correctly. But now I'm going to have to use integration by parts again, so here we do it all again. Now I'm going to let u be equal to 2x and let dv be equal to e to the x dx again. And we're going to have, we're forced into du is equal to 2 dx, and v is equal to e to the x. So running through this, now we're going to have x squared e to the x minus, now that integral becomes, all of this becomes v times u, so that's going to be 2x e to the x minus the integral of v du, which is just 2 e to the x dx. Close those parentheses. Now what I want you to notice is, as I've done this, I've done 2 iterations, I'm obviously going to have to take this negative and distribute it in. And keep that in mind, because I'm going to refer back to that later, because it ends up changing every sign the other way. So what I have now is this. I've got x squared e to the x minus 2x e to the x, and then I have plus, because I distribute the negative in, plus the integral of 2 e to the x dx. And all of this, I think it's fairly obvious, becomes x squared e to the x minus 2x e to the x plus 2 e to the x plus a constant. Now technically with the constant, every time you integrated you would have had a constant, but let's just pretend that we had the constants, we summed them all up to get another constant. So there it is. So there it is. And I just want you to notice that the sign keeps on switching. Positive, negative, positive. Now it's not that we're always going to get positive, negative, positive for any example other than this one, but just keep in mind that because every time I do integration by parts, I end up having to subtract an integral and I have to distribute in the previous subtraction. So now what I want to show you is this. Let's take the original problem, okay? And let's make a column. We'll call this column u, and we'll call this column dv. We're going to let x squared be in the u column, and we're going to let e to the x be in the dv column. What we're going to do is we're going to differentiate this column, and we're going to integrate this column. So let me scroll up a little bit. Now I don't want to lose the answer. I want to keep the answer right there so that we can see it. Okay, now watch. If I just keep differentiating, this is 2x, the next derivative would be 2, and the one after that would be 0. That's how I know to stop. Integrating. Now I picked e to the x because it's so easy. It's e to the x, the antiderivative of the x is e to the x, and the antiderivative of the x is e to the x. Now I want you to notice the first term in our answer is x squared e to the x, and the first term here, if I do this. And if you'll notice, if I connect them diagonally, it matches up with all of my terms. The next one is 2x e to the x. The next one, over here. This is the first one, this is the second one, this is the last one. So if I multiply these things together, I get, just doing it piece by piece without putting the sign in, I get x squared e to the x. That's this one. The next one I get 2x e to the x. And then the last one I get 2 e to the x. Now here's the rule for the signs. This is what it comes back to. On the first one, I'm going to denote that with positive, meaning I don't change this. I don't mean it's going to be positive. I mean I'm not changing the sign. This I'll denote with negative because I changed the sign. This I'll denote with positive because I changed the sign. So what happens? X squared e to the x, leave the sign. 2x e to the x, change the sign. So instead of positive, it's going to be negative. 2 e to the x, leave the sign, and it was positive, so I'm just going to leave it. And don't forget to always add your plus constant. So there it is. Okay? Now, let me scroll down, and let's do the same example without going through the trouble, and just do the column right away. So let's take a look at this one. This is going to be integral of x to the third e to the x dx. Okay? So according to our method, it's going to be this. Let's make a column for u and a column for dv. I think it's obvious what I'm going to do. This is going to be x to the third. This is going to be 3x squared. This is going to be 6x to the first. This is going to be 6, and then we stop at 0. In this column, it's going to be e to the x, e to the x, e to the x, e to the x, e to the x. Now let me just be clear. In this column, I'm actually integrating. I'm not differentiating, because remember, if you have dv, you keep going backwards. Now, here's what I'm going to do. Multiply those things together. This one stays the same. Change the sign. Stays the same. Change the sign. So my integral is going to be this. X to the third e to the x. 3x squared e to the x. Change the sign. Don't change the sign. 6x e to the x. Change the sign. Minus 6 e to the x plus c. And you can check when you differentiate this. You're going to be left with, and I highly recommend you do check, but you're going to be left with 3 x to the third e to the x. And don't forget, when you do, it's a pain in the neck because this, to differentiate, requires you to use the product rule a whole bunch of times. So it's slightly irritating, but I definitely think it's worth going back through and making sure that you understand it. So at any rate, the way this works, you can use this tabular notation if one of your functions is a polynomial that degenerates when you take its derivative all the way down to 0. And there it is.